So this is number 11, 4.1. So you're gonna compute the linear correlation coefficient for each data set. Okay? So let's pop open that data and copy it into StatCrunch. When you see these little, it's like a little double box over next to the data. So you use the little circle thingy where it says click the icon, and then if you you notice there's this little bitty box, and if you click on that, you can copy the data into StatCrunch, which you want to do.
What number is this?
11. 11. So notice it says open in StatCrunch. So if you do that, there's the data set. Okay? And it gives you x1, y1, x2, y2, so on and so forth. So it's telling you, you've got 4 data sets there. X and y1, x and y2, 3, and 4. So recall that our whole linear correlation is through, you click stat and down to regression and over to simple linear. Stat, regression, simple linear. And for the x variable, let's click x1 and then y1. And now you guys might have different numbers, right? Different problem, different numbers. And then that's pretty much all you need for right now, because all they want is the R value. So all you have to do is give it your, select the correct x and y, and then notice that there's your R, your correlation coefficient. So it's like 1, 2, 3, 4, 5, 6th row down, and it looks like the correlation coefficient is negative 0.816. Okay? So then you would go through the 4 data sets. I'm assuming that they're going to ask you something about which has the best fit, something like that. Remember that the closer R is to either positive or negative 1 is going to give you the better R value. Okay? Closer to either plus or minus 1. Because remember, the closer to negative 1 simply means that the data lines up more closely in a negative fashion, like if it had a negative slope. And the slope in that case will have a negative line. So the sign of the slope, remember, plus minus, and the sign of the R value is always going to be the same. Okay. Because again, the linear correlation coefficient is an indicator of the strength of the linear relationship. So those always match. Does that help, Melissa?
Yeah. Thank you.
You're welcome. Ashley?
In chapter 3, one of the I can't pull it up, but one of the problems had you find the z-score for like 10 different things. Is it like a quicker way to find the z-score than like
Yes.
doing it by hand? Okay.
Yes. Yes. Did you do it for all of them?
I got like halfway through and was just,
Forget this.
yeah. It took like almost an hour.
Yeah, there is. You can actually. Mariah, did you and I work on that together? The z-score problem. Yeah. And you had to use the population standard deviation, as I recall. Is that right? Okay. So are we good here? Okay, cool. Do you remember what problem that was, Ashley?
No, and it's not letting me open it.
If you go back to your grade book and go to that section and click review, you can go back. Oh, and gang, when you take an online quiz, you are able to go back and review your quiz after the due time. So we do Wednesday, Thursday for you guys. So after Thursday at midnight, you can go back and review your quiz. Okay? So yeah, if you go to your grade book, sometimes it's It feels like you can't go back and review, but you have to go in again through the grade book or through your main menu. If you click on where you have that course timeline, and in my account, I don't have anything there, but where you have your little icons, there are your different assignments. If you click on those, you can review that section as well. Okay? But again, if you go to gradebook and your
Section 3.4, number 6.
okay, so if you go to gradebook, you should have your assignments there. I don't because I haven't done any of the assignments. My bad. But there you should have the opportunity to review. Is that what you did, Ashley?
Yeah.
Okay, cool. Do you mind if I go to your problem? Okay. So it's 3.4.
Number 6.
3.4, number 6 is where we're headed. Yeah, and I'm glad you brought this up, actually. This is really good review. We'll use Z-scores through the whole semester. Z-scores are really important. Okay, so here we have the accompanying data represent the pulse rates of 9 students. Treat the 9 students as a population, that's key. Compute the Z-scores for all the students. Compute the mean and standard deviation of the Z-scores. Okay? Okay, let's do this. So, you can write a little expression in here to do all the calculations at once, okay? So the first thing we need to do, because I'm not sure, anyway, I'm not sure if you're able to calculate the standard deviation from the data in this little code, right? So let's go ahead and find the population standard deviation, okay? And so let's click to open that data. And again, this is 3.4, number 6. Well, actually, okay, so there's the students, there's their pulse rate. Let's click that little box and open that puppy in StatCrunch. Okay. So there's our 9 students, all their pulse rates. So recall that all of our summary statistics, mean, standard deviation, 5-number summary, median, mode, all that stuff, is through, you click stat and down to summary stats. And all of these calculations that we've been doing in Chapter 3 are called summary statistics. Okay. So let's go down to summary stats and over. Z-scores are also summary statistics in a way. We go down over to columns, and let's click our pulse rates. Now remember, this is a population. They're telling us to consider this as a population. So let's pick the unadjusted standard deviation. Okay. And compute. 7.67069. Seven point 67069. 14. Okay. This is the one piece, this standard deviation, that I couldn't get the little code thing to do on its own. So got to figure that out first. Recall that Z-scores are given by x minus mu divided by sigma. So we take each data value, we subtract the mean of that data, and divide by the standard deviation of that data. You can also z sample data. So that would be x minus x bar over s. Okay, so let's do that. If you go to data and down to compute over to expression. Data, compute, expression. So what we're going to do is write a little itty bitty line of code that's going to allow us to calculate all those z-scores at once. Okay. Then you click build. So what we want to do is write a line of command for this thing that tells us to z all of our data. So when we choose the pulse rates as our x, it's going to do a calculation for every one of those. All right, it's going to be important to put the numerator in parens. So let's start with the set of parens. So click that, and you'll see the parens pop up. So the little code we're writing is going to show up on this top line, right under where it says expression. So click your parens, and now we want our x's, which are the pulse rates. So click pulse and add column. You'll see it pops into the parens. And then we want to go minus the mean of those values. So click the minus, it's in the little calculator expressions, the blue buttons on the left. Then this thing will calculate the mean and stick it into the formula. So over on the right where it says functions, they're in alphabetical order. So scroll down to where it says mean, click on that and add function. You'll see another set of parens open after the command mean. So it wants you to tell it which data you want it to find the mean of, which is the pulse rates. So again, where you have pulse selected in that middle box, you're going to go add column. So we have our numerator, the pulse rates, minus the mean of the pulse rates, and then we're going to go divided by standard deviation, which is that thing. So take a couple of right-hand arrows to escape out of the parens. Click the divided by over in the little, so once you get used to the way this thing works, it's fairly easy, as long as you think the way it thinks. So you're going to take a couple right-hand arrows, escape those parens, add the divided by, and then you're going to type in that number, 7.670. And now you might have a different standard deviation according to your data. This is Ashley's data. Okay? So let's see, 7.6706. And I want to use all of the digits because if you round, use that rounded number in a formula and then round your output again, chances are you'll be off enough decimal places to make your answer incorrect. Okay? So again, does this make sense? You guys with me? So you're taking the pulse rates, you're subtracting the mean of the pulse rates, that's mu, and you're dividing by the standard deviation of the pulse rates. I couldn't find a population standard deviation command here. So I had to calculate that standard deviation. And then you're going to click OK, and it's going to put the expression in that little box and then compute. And you'll see that all of your all of your z-scores are in the third column there. All of your z-scores. So remember that z is the distance in standard deviations specifically that each value is from the mean. The distance in standard deviation. We learned by the empirical rule and Chebyshev's theorem that almost all your data should be within 3 standard deviations, about 3 standard deviations. So if this is the case, you can expect all z-scores to be between plus minus 3. Okay? Plus minus 3 standard deviations from the mean. Now, when a score, we're treating this data as a population, okay? When you z the whole data set, okay, it takes it and it's like a formula where, say, you would what's the word I'm looking for? It's like a formula where you would take miles and convert that to kilometers, or gallons and convert that to cups, or something like that. It converts the data over to a new distribution. And a z is a specific distribution. When whatever values come out of there, the mean of the z distribution is 0, and the standard deviation is 1. The standard deviation is 1, and that's why all the values are between, all the z-scores should be between plus minus 3. Plus minus 3 with a standard deviation of, let me rephrase. Plus minus 3 standard deviations with a standard deviation of 1 from the mean of 0 should be plus minus 3, yeah? Right? Yeah? Yeah? Right? Does that make sense? Right. Okay. So, yeah. So, again, all your z-scores, bless you, have the mean of all the z-scores is 0, standard deviation is 1. So again, all of your z-scores should be between plus minus 3, which is saying that all of the data is within 3 standard deviations of the mean. Okay? So let's now take this data. It says to find the mean and standard deviation. Bless you.
Thank you.
Find the mean and standard deviation of the z data. And we would typically round z to 2 decimal places. So to find mean and standard deviation, we're going to use summary stats. Okay. Just as we did before. Salute.
Thank you.
And we'll click now the z-scores, which is pulse minus the mean of pulse, blah, 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 blah. And then
Sorry, guys. Sorry. Allergies.
yeah, terrible, huh? Okay, so the mean there of this particular data set is negative 7.79 times 10 to the negative 17.
Thanks.
Oh, 16. Whatever. So that is pretty darn close to 0. Remember, negative 16 as a decimal point, it takes this decimal and does what with it? Moves it to the left. How many places? 16. So this number is negative 15 zeros, 7.779, whatever. So really darn close to 0. Check out the standard deviation. Oh, you know, we should have probably gotten the unadjusted. It probably would have been closer to 1, but you can see the standard deviation is 1.060. So really close to, oh, actually this is S. Really close to 1. And every time you will get that. Okay? So z-scores. When you convert data to z, you will be in a distribution with a mean of 0, standard deviation of 1. Okay? I'm glad you asked that. That was good review. It's good stuff. Good stuff.
You know,
Yeah.
number 12 ones.
Sure.
4.1.
4.1?
Yeah, it's like comparing 3 rows and it's saying which one would you choose.
Okay. And I'm sorry, remind me your name?
Alexis.
Alexis. Thanks, Alexis. Tigers, right?
Yeah.
So that's number 12? Okay, so we're in 4.1, number 12. 4.1, number 12. Oh, okay. Okay, now, again, when we're doing homework problems here, recall that you're, you know, if you decide to work along with me, your numbers are gonna be probably a little different, right? So bear in mind, okay? So suppose the data represent the annual rates of return for various stocks. Okay, if you only wish to invest in 2 of the stocks, which 2 would you select if your goal is to have one stock go up when the other goes down? In other words, you want a rate of return from one or the other. So if one's going up, it's okay if the other one is, you know, well, if one is not doing well at all, you would want the other one to be going up, and vice versa. So that would be an inverse relationship. So what we want to do we want to look at the we could look at the scatter plots of each pair. So we want to graph one against the other and see which one has, okay, if we want the best, representation of when one stock increases, the other decreases. So we're looking for some kind of a negative linear relationship. So I think what we'll do is we'll look at R values for each group of 2, and based on that we can decide which pair is better. Or we could look at R values. We can do it with R values too.
You don't think it'd be okay to like just try to compare the numbers that are on those lists and see one's higher, one's a little bit lower, but not too much lower, and kind of compare it at least like maybe?
Yeah, well, you can see, okay, you can see that B is always decreasing. Why would you invest in that? Okay, I guess you got a lot of money and you don't want to make too much income because then you pay too, I don't know, why would anybody invest in anything that goes down? I don't understand, but we'll just do the problem. Okay, so I would want to prove that numerically, Jen. So Jen says, why don't we just compare the numbers? Because we want to prove it mathematically. But you might do that. So what I would do, I think I'm gonna look at R values. Let's look at R values, Alexis. So again, you've got that little box up in the corner by the data. If you pop that open, you can open your data in StatCrunch. Now we want one going up when the other goes down, specifically. It looks like B is the only one going down. Do you agree? In Alexis's case, anyway. You guys might have different values, you might have negatives in a different column. But I think what we wanna do is compare A and B and C, and see which one has the stronger R.
So what does the
That's my
R
guess.
really tell us?
It tells us the strength of the linear relationship. So specifically, if this person wants, one to be going up when the other is going down, the stronger the R value would tell you that that relationship is happening the best.
Okay.
Yeah. So, let's go stat and down to regression, simple linear. And then for X, let's choose A. For Y, let's choose, let's see, increasing and the other's decreasing, yeah. Let's choose B. Okay, so, I'm gonna choose A for my X and B for my Y, because he wants one increasing when the other is decreasing. And we've got an increasing and decreasing pair. A is increasing, B is decreasing. And then compute. Okay, it looks like there we've got an R value, a correlation coefficient of negative 0.755. Okay, now let's go back. If you go to the little options window in your output, in the above left of your output, you can go back without having to go through the previous steps. You can go back into the menu and change settings. So the B is the only one going down, so I think, if we choose the X variable to be C, now again, we've got one variable increasing and the other decreasing. So I think those are the only two pairs that it would make sense to look at. Compute. There we have a relationship of negative 0.992. And that gives us the stronger relationship if you want one increasing while the other's decreasing. Does that make sense, everybody? You with? So if you want that specific thing to happen, you want the stronger R values. And again, remember that a smaller, this number is smaller than that number, right? It's a smaller number. But remember, you want closer to either negative or positive one. Either direction gives you a stronger linear relationship. Yeah? Yeah, we cool? We good? Okay. Anyone else? Questions? We can, Alexis, did that do it?
Yeah.
Cool, you're welcome. Oh, and I'll have lab 3 up, ASAP. It's all about regression. Okay, cool, go. Let's go back and, and this is nice, is you guys have some questions this morning, because we can kind of go back and talk about some of our regression steps. So we have our paired sample data. First step, we graph it. We look at the graph, decide whether or not we think it would be a good candidate for linear regression. If it looks pretty good, we proceed. We calculate our R value. And remember, R gives us the strength of the linear relationship. So it gives us an indicator or an indication of how good that relationship is going to be. We calculate the regression line. The regression line is a descriptor of that specific relationship. Okay, it describes the linear relationship itself between the paired sample data. And the regression line is our tool for predicting what a value of y will be given a value of x. And that's really our goal. That is our ultimate goal. Given, the values of x and y, and say, here's our data. If after this, after we use this data to describe this relationship, if I've got, an x value here, what is going to be, what is going to be the predicted value of y? That's ultimately what we want. We want to use this thing as a tool to make predictions. Okay? Remember that we only use this tool within the bounds of the data that we're given, because we don't know what happens outside of that realm. Okay? We don't want to extrapolate outside of our realm of sample data. And again, why? Because we don't know what happens out there. We don't have anything that describes that. Okay, so we do that. Oh, remember that we want to talk about the utility of the y-intercept. Does it have meaning in our process with respect to what we're doing? We want to talk about what the slope means with respect to the problem. Okay? We want to generate residuals. We want to generate the residuals. Another horrible formula, but we can do that with SecCrunch. And we want to find the sum of the squared residuals. So remember that you don't have to calculate the residuals by hand. And remember the residuals are let's say that this is our regression line. The residuals are the vertical distances between each data value and the regression line. They measure the error of the model, what's going on in the model. Recall that if a residual is positive, it's actually an underestimate. If it's negative, it's an overestimate. And we can talk a little bit more about why that is. And then in 4.3, there's a couple more numbers that we want to look at that have meaning with respect to our whole process here. One is called the coefficient of determination. And we'll talk about what that means. I don't think we got there last time. I think we just got to residuals, didn't we? Yes. Yeah, okay. Thank you. And we actually also want to look at a residual plot and talk about what that means. Okay, so as I recall, last time we had some Bayer data. We were working with some Bayer data. That data we can find for 128. So you'll find that in StatCrunch.